How are you, everybody who loves advanced chemistry? How are you, lovers of advanced chemistry? How are you, people who really enjoy the presence and the discovery and the innovations of the classical and modern chemistry? Here, my name is Olenjolai from beautiful country that call it Tanzania. I'm a Tanzanian and this is our national flag beside me because I love so much my country and I'm conducting these programs in my country. And just to tell you in advance, these programs I'm really focusing on the curriculums of United Republic of Tanzania for advanced education. So whether you're national and international students, you have to stay tuned. You're warmly welcome into our fantastic online school that's called Tanzania Online Advanced Secondary School in square bracket OLENJOLAIM. That's not enough. I would like to welcome you into one of our YouTube channels that's called Tanzania Online A-Level Secondary School in square bracket OLENJOLAIM. So with these fantastic online advanced schools, we are real here to help you, and we are really here to answer your questions, and we are really here to solve all the problems that you're encountering through your process of learning. So the first question that you're asking yourself, what are we doing? What the vision that we have? Because the word of God says in Proverbs 29 verse 18, where there is no vision, people perish. Where there's no vision, Tanzania Online Advanced Secondary Schools is going to perish. So the fundamental assignment that will be given from the Lord, our manufacturer himself, he gave us an assignment to train and teach some of the students in Tanzania and internationally. It means that non-Tanzania, some of the Tanzanians and none of the Tanzanians who will be ready to extract knowledge and wisdom in advanced chemistry. It means that in advanced chemistry and physics, and also in advanced mathematics and basic applied mathematics. And they combine that knowledge with the knowledge and wisdom that you're going to extract from the Word of God written in the Holy Bible in order to solve real life problems. So the main objective of Tanzania Online Advanced Secondary School in square bracket OLENJOLAIM is not to help you in order to pass your midterm test or your annual exams, or maybe your pre-mock exams or mock exams or NECT exams or advanced certificate secondary education examination paper 1, paper 2, paper 3. That is not our main objective. Those are our specific objective. Our main objective here is to see our continuing students and even our graduating students solving real life problems, because that is the main objective of education. So in educations, we extract knowledge, wisdom, and understanding in order to solve real life problems. Because believe me, believe me that there's a particular problem that waiting you, whether from your community or whether in your country or in your city or in your family, even your own problems also you can solve by using the knowledge of advanced science and even also by using the knowledge of advanced mathematics. So that's an assignment. But I know possibly who is watching this program right now, possibly you are an advanced secondary students. You're warmly welcome. Possibly you might be a parent or you might be a guardian. So you might be a sponsor who have children who are doing their advanced studies in science or in some of the combinations which actually that is study 6 combinations in Tanzania where we have students who are studying advanced chemistry. So I'm happy to have you today. Stay connected, stay tuned. I would like you first, the second thing that I want to let you know, whenever you go any physical schools, whether you go pre-form 5, when you join to a form 1 school, a secondary schools, then the first thing you met with is called something we call registration. Okay? So in registration, so how do you get registered in Tanzania Online Advanced Secondary School? So OLENJOLAI would like to unlock, because we want you to be registered permanently from the beginning of your advanced studies to the end of your advanced studies. So believe me whether or not, in every session, I'm going to teach non-extraordinary. I'll be going to teach uniquely and in a very excellent and in a very achievement way, okay, in very excitement and entertainment way. But every session is an event, and believe me that I will be convincing you day after day to fall in love with advanced chemistry, with advanced physics, with advanced mathematics, with basic applied mathematics. I used to do the same myself, that I always love these subjects and advance myself because I don't know everything about them. Okay, so the first thing, the first step for you is you should have what you have a Yahoo or a Gmail. Have a Yahoo or a Gmail. Okay. So the second step, we ask you to sign in YouTube, right? YouTube, sign in YouTube by using your email. So by using your Yahoo or your Gmail. That's the second step. The second step, after you sign in YouTube, then go into TANZANIA Online Advanced Secondary School, the square bracket Olenjolai. So that's right, this name. So it's means that write this name, TANZANIA Online A-level safety school in square bracket OLENJOLAIM. Afterward, when you go there, you'll see the buttons which have been written as what? Subscribe. Okay? So this button has been written subscribe. So click these buttons only once within just a second. So once you click, when you click, its color of its background color changed and also its text changed and the words read as subscribe. And then you see the icons of the bell. If you click, you see all. Okay. So after you follow those 4 steps, you have been registered for the rest of your life. You are not required to subscribe once again. You just subscribe once. Maybe the word subscribe, it's a new term, but this is a term from English. What the means of subscribe? Subscribe, from the English dictionary, it means that give me notifications when a new product is being announced or is being released. So here we have products, and these products we call them session. Okay, we call them the lecture videos, the live lecture videos. So once you subscribe, you will get notifications when you are online that Olenjolai has added a new session in his own channel. And believe me or not, we have a strategy, we have a plan. This is our daily plan. Every day, during the evening hours, around 4 p.m., we used to publish at least 1 video in our YouTube channel in order for you to go through it the whole night, even the weekend, even the holiday times, in order for you to get transformed. Okay, so that is kind of enough. Remember also we have TANZANIA Online Advanced Library, where we have materials. For example, this is conceptual chemistry, or we call it Chandi 1. It's the famous book. You can order this book online. Just go to the descriptions, which is a link. But also we have copy of some other books. For example, this is Ngaiza, means it's called the Atomic Structure and Bonding by Ngaiza. And also we have questions and answer books. Okay, this is this certificate secondary education examinations, examination paper 1, advanced chemistry paper 1. So it comprises questions from 2001 to 2016 and solution. But also we have another weapons or another reference material, which is advanced certificate secondary education examinations paper 2. This comprises questions and solutions from 2003 to 2018. So you can order a package of all of these books. You can order also, we have a scientific calculators, original ones, for example, Casio function 991. So you can order all of this entire package and you can send in any region of Tanzania, okay, with a very minimum cost, and you can order it with a very reasonable and minimum cost compared to the cost that these materials are sold in the local shops. So don't miss it. Make sure that you have these materials, because myself as a teacher, I'm going to refer this material and use them in every session to impact the knowledge in your mind. So even yourself, I'll give you also some homeworks that you have to go through these books and collect this information and solve those questions in order for you to be prepared with this. So let me solve your problems right now of understanding advanced chemistry. We are in departments of advanced chemistry. Here we are teaching 2 subjects, advanced chemistry from 1, 4, 5, and advanced chemistry from 6. The subject today is advanced chemistry. So we have some main topics. One of the main topics is called general chemistry. In general chemistry, we have 2 topics, One is called the atom, and the second one is called the chemical body. So today, these contents are the class for the pre-Form 5 and also Form 5 students, or class 13s or high school students, and even also are relevant for the Form 6 students who want to review or to do the review in order to be prepared for the Advanced Certificate Secondary Education Examination. But it's not the only target, but also to get prepared on solving real life problems. So ladies and gentlemen, let me do the quick review of session 4E, session 4D. Okay, remember that I said I jumped in some of the materials when I was teaching general. So I jumped in some of the material from session or from lecture 3, just bring it to lecture 3, but we can change it from session 3 to session 5. So when I jumped, I did a small estimation. So when I did a wrong estimation. So that's why that in between here, now we are going to have session 4A, session up to until we finish this concept. We might even go to up to session, maybe session 4L. So you have to understand the meaning. So the issue is, whenever you find that you are covering the contents for session 4, you have to make sure that you go session 4A, session 4B, session 4C, and even also some other lectures or sessions are organized in terms of A, B, C, D, or A, B, C, D in some of the cases up to D, but commonly A, B, and A, B, C. Okay, those are the common division. But in those other lectures, we just break down into the small, to make videos into small. But for this one, it's a complete session. We don't break it down. So in session 4D, we taught you about definition. What is the meaning of hydrogen spectrum? So we taught you what the meaning of hydrogen spectrum. We define it, and then hydrogen spectrums. And then the next question we ask ourselves, how can we produce? How can we produce? We say that we produce by allowing what? High voltage to pass through the hydrogen, through the tube, okay, the tube which contains hydrogens under a particular condition. And then we say that in hydrogen spectrum, what happens? We say that means there is a spectral emissions. When there is a spectral, either spectral emissions or spectral absorptions, we are going to have spectral lines. So we discussed about spectral lines that we can have. So in hydrogen spectrum, we say the spectral lines are energy levels. So we call them also the energy levels. So we say that when electrons, okay, so we mentioned that we have Lyman, we have also Balmer, okay, we have Balmer, we have Paston, etc., P-funds and bracket. Okay, so in this one also, before even we advanced, we defined about Rietveld equation, okay, Rietveld equation, which you said 1 over wavelength is equal to Rietveld constant, then 1 over n1 square minus 1 over n2 square. So that's what we have introduced to you. We tried to express in wave number, in frequency. We didn't go too much in physics, in atomic physics, you have to go too much and think about energy and etc., etc. And even later on, we'll advance this Rietveld equation. So again, we discussed with you about the ground state, okay, ground state. So you can access this session 4D in our YouTube channel. Ground state, what it means of ground state, we say that this is the stable state, okay, and its number, it means that its energy level is n is equal to 1. Then we discussed about excited state, okay, excited state, and then we discussed about the infinity region, but before infinity region, we discussed about convergence limit, discussed about convergence limit. So that's what we have, so infinite regions and the convergence limit. So we ended there, and then today we have to continue with the session 4E that called Rietveld equations of hydrogen spectrum, and we are also going to solve some problems, so you have to stay tuned. So if you open the book of conceptual chemistry in the chapter of the atom, page 154. Then I want to discuss the applications of the Riemann equation in the study of hydrogen spectrum. So let us start. So we say that a Riemann equation can be used to compute wavelengths or frequency or energy of electrons when it falls. We discussed about excitation. When it falls from what? From any energy level to what? To the lower energy level. Okay? Energy level. So before I explain to you the applications, let me show you the hydrogen spectrum diagram. The hydrogen spectrum, when we visualize it from spectroscope, the hydrogen spectrum start with what? Infinite region. Dotted line, infinite region, when n is equal to infinite. Then there are closed lines. These are higher energy level lines. So remember, hydrogens contains what? Contain one electron. Okay. So you have to enjoy the beauty of advanced chemistry, and also you have to remember that in case you feel from your heart that you want to offer God your free will in thanksgiving, don't hesitate yourself to send your free will in thanksgiving through that telephone number, and your free will in thanksgivings will be paying the running cost for this program to be in air. Okay? So we have these energy levels. Okay? So suppose that this is the hydrogen spectrum. Okay? So here we have n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, n is equal to 5, then n is equal to 6, etc., etc. And then the last one is n is equal to infinity. Okay. So this one we call it Riemann series. To remind. And this one we call it what? Balmer series. Balmer series. And this one we call it Pascal series. Pascal series. Next one we call it bracket series. Then the next one is P-fan series. P-fan series. So ladies and gentlemen, this is figure, I think it was figure 4, whatever, 4.1 if I'm not mistaken. So this is the hydrogen spectrum according to what has been drawn in the conceptual chemistry, in the book of conceptual chemistry, as you see. But also you have some transition lines. Okay, so that's page 156. You have some transition lines to find electrons falling from here to here. So you have to label it. So you see, so again, we have electrons falling from here to here. Hence, electrons can fall from here to here. Okay, hence the other ones can fall from here to here. And, okay, excuse me. So electrons can fall from here to here. And electrons can fall from n is equal to 4 to n is equal to 2. Electrons also can fall from n is equal to 3. Electrons also can fall from n is equal to 5 to n is equal to 3. And electrons also can fall from what? N is equal to 6 to n is equal to 3. then here we are. Electrons can fall from n is equal to 5, n is equal to 4. Even also, but when electrons reaches to infinity, it won't fail, it won't fall. So these are the transitions. So another thing which we have to add to you today is you have to relate the Lieberman equation with these lines. First of all, we have to define what means of Lieberman series. So Lieberman series, the spectral lines of the series are produced when electrons jump from the second or third and higher energy levels to the first energy level. Okay? So we have the first one, we call it Lieberman series. Say Lieberman series. Ladies and gentlemen, say Lieberman series. Okay? So question 1 for this session. What is Lieberman series? What is Lieberman series of hydrogen spectrum? I left the homework for you, if you do remember. I left the homework for you. I believe you've done. In case you find any challenge, please let me know in the comment section. What is a Lieberman series? Okay, ladies and gentlemen, Lieberman series is a series of lines, according to social chemistry, is a spectral lines so is a spectral lines which are produced when electrons jump or in other words fall from what? From secondary or third or fourth or higher energy level, we are not here in the higher energy level, or any other higher energy level to the first line. And this first line is where n is equal to 1. That's how Lieberman series is being formed. Remember the steps for you to get registered. So Lieberman series is a spectral lines which are produced when electrons jump or fall from secondary or third or fourth or any higher energy level to the first line where n is equal to 1. So this is what we call Lieberman series. So when electrons fall from n is equal to 2, this is the second line, this is the first line, second line. Okay, so we can label this is first line, but this is first line in general. Okay, first line, second line, and this is the third line. Okay, this is the first line, etc. But this is the first line of Lieberman, and this is the first line of Balmer series. Okay, so we say that from that concept means when electrons fall from n is equal to 2 to n is equal to what? So let me just give you space in order for you to see. When electrons fall from n is equal to 1 to n is equal to from n is equal to 2 to n is equal to 1, then we form a Lieberman series. Or when electrons jumps from n is equal to 3 to n is equal to 1, we form a Lieberman series. Or when electrons fall from n is equal to 4 to n is equal to 1, we form a Lieberman series. Or even when electrons fall from n is equal to 6 to n is equal to 1, we form a Lieberman series. Then, if that the case, remember that these series are equivalent to certain equivalent species spectrums with different with the spectrum of the light. Okay, spectrums of light. So we say that okay, so the frequency in that was before we go to the we call that this is So we say that if any supply is in ultraviolet light, V regions. Okay, so so it is, again we say that this one, it is in UV region, ultraviolet region. Okay? So we say that now, if that the case, we say from a rebate equation, which is what? 1 over wavelength is equal to rebate constant, 1 over n1 square minus 1 over n2 square. Okay? So from this equation, we say that for Lyman, the rebate equation of Lyman series, the rebate equation for a Lyman series is given as what? As when n1 is equal to 1, but n2 it can take any value. So now 1 over wavelengths, rebate equation will be defined like this one. So here we have what? 1 over 1 square minus what? Minus 1 over n2 square. So ladies and gentlemen, we say that 1 over wavelengths of electrons of the spectral lines in Lyman series will be 1 minus 1 over n2 square. Okay, so this is the equation. Okay, so that's the equation. Excuse me, I didn't plan to read this. So n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, and this is n is equal to infinity. Here we have n is equal to 5, n is equal to 6, just like that. Transition. Okay. So this is the diagrams of hydrogen spectrum. I don't expect to erase it because we need hydrogen spectrum. Okay. So then we go for the second line, spectral lines, which is called the Balmer series. Say Balmer series. Okay. What is Balmer series? That the next question. This is the second question. What is Balmer series of hydrogen spectrum? So simply say that Balmer series, ladies and gentlemen, my beloved students, Balmer series is a spectral. Is a spectral lines. Is a spectral lines which are produced when electron jump or fall, electrons jumps or falls from third or fourth or fifth. Then we have to continue here or fifth. I believe that not these instructions for you to get registered permanently. Okay. So, or any other energy level. Energy levels to and to second dot. So this one to secondary line, where n1 is equal, where n is equal to 2. So the Balmer series is formed when electrons jump from n is equal to 3 to n is equal to 2, or when electrons fall from n is equal to 4 to n is equal to 2, or when electrons fall from n is equal to 5 to n is equal to 2, or when electrons fall from n is equal to 60 to n is equal to 2. Okay? So that is the definition. So we say Balmer series. Balmer series is the visible spectrum. So this we call the visible, called the visibility. So this we call the visible spectrums. Okay. So visible part of the line spectrums. Okay. So this is the LSA place in wavelength lengths in the visible spectrum. So this is called the visible spectrum. So sometimes in questions you hear that electrons just jumped from maybe n is equal to 6 to the visible spectrums. So you have to know that that is all about Balmer series. So you have to know Balmer's and also its name. It's the second name, which is visible spectrum. So we say that from a Riemann equation, so we say the Riemann equations, we have the Riemann equation on the blackboard. We have recorded the Riemann equation. Riemann equation of what? Of Balmer series. Of Balmer series is given as what? As 1. So it's given as what? As 1 of what? So 1 over wavelengths is equal to Riemann constant, then 1 over what? Over 2 square minus what? 1 over n2, any higher energy level. So simply say that 1 over wavelengths, this is equal to what? Riemann constant. Then here we have what? 1 over 4 minus what? 1 over n2 square. 1 over what? n2 square. 1 over n2 square. So this is the formula to find the wavelengths of what? Wavelengths of Riemann constant. So it is 1 over wavelengths is equal to Riemann constant. Then this is 1 over 4 minus 1 over n2 square. So this is the standard equation of Riemann, or it is the standard equation of Riemann equation when electrons jumps from when electrons jump from higher energy level into the Balmer series. Okay? Into the Balmer series. Okay? So then, the 30 spectral lines that we have to discuss is Bastian, and the fourth is bracket, and the fifth is prefund. Afterward, we have to solve problems right now. So, ladies and gentlemen, let me now teach you about Bastian series. Say Bastian series. I'm teaching you in a very different way. This is tough. It's quite different from how I learned. I spent several months to understand. I think I spent more than a year to understand this hydrogen spectrum. Okay? So, these are the collections of hard work hardworking of several years. Question 3. What is past tense series? What is past tense series? What is past tense series? Okay. So past tense series. Past tense series, we say that is a spectral line. Okay, is a spectral lines. So these are the spectral. These are the spectral line, not is. So even there we have to change. Past tense series are the spectral lines. Are the spectral lines which are produced when electron, young or false from what? From 30 or 4th or 5th or any other higher energy. Okay? To what? Okay, and other energy to 3D line whereby n is equal to 3. This is how past tense series is formed. In other words, past tense series is called or is formed it is in infrared region. It is in infrared region. So we say that for past tense series, so in regards of V&Vi question, N1 is equal to 3. So now 1 over wavelength is equal to V&Vi constant. Then we have 1 over 3 square minus 1 over N2 square. So now the V&Vi question of past tense series. Past tense series, this is 1 over wavelengths. This is equal to V&Vi constant. Then we have what? 1 over 9 minus 1 over N2 square. Okay. So that is the standard equation of what? That is the standard V&Vi equation of past tense series. Ladies and gentlemen, let me now teach you the first line, which is bracket series. So let us now learn about bracket series. Bracket series. Bracket series. So the fundamental question is, this is question 4. What is bracket series? What is bracket series? What is bracket series? Okay. So bracket series, we say that simply the spectral line the spectral lines formed when electrons when electron jumps or falls from fourth, no, from, and this one is, it's not correct, from fourth. So start from fourth. Fourth office or any other higher energy level. So here from fifth or sixth or any other higher energy level. Any other higher energy level to what? The first line. And this first line, when n is equal to 4. So this we call it bracket series. Bracket what? Bracket series. So now, for bracket series, n1 is equal to 4. N1 is equal to 4. So therefore, the equation now will be 1 over wavelength. Here we have Riemann constant of 1 over 4 square minus 1 over n2 square. So 4 square is equal to 16. So now this general standard equation of bracket series of hydrogen spectra is given as follows. I believe that you are still enjoying. Remember to order books, scientific calculator, notes online by clicking the buttons which has been written here, show more, so that you'll see our resources that we can ship to you, or we can ship to you online once you place your order and you pay for it. Make sure that you get our materials that will help you to go or to learn further. So 1 over wavelength is equal to Riemann constant. So we have 4 square, that is 1 over 1 over 16, minus 1 over n2 square. So this is the general equation. Okay? So this is our general equation. Okay, so ladies and gentlemen, right now let us enjoy the beauty of P-Fund series. Stay with me, P-Fund series. Okay? P-Fund series. So this will be question 5. What is P-Fund series? What is P-Fund series? What is P-Fund series? So P-Fund series is a series, or is a spectral, the spectral lines, plural, the spectral lines, So P-Fund series are the spectral lines. Are the spectral lines formed when electron jumps or fall from 6th line, 6th or 7th, or any other higher energy level. Any other higher energy level to the 5th line, where n is equal to 5. So we say for P-Fund series, the first energy level in 1 is equal to 5. So if that the case, 1 over wavelength is equal to Riemann constant, then we have 1 over 5 square minus what? 1 over n2 squared. Okay? N2 squared. Okay. So if this is the case, you say that 5 squared it is 25. So the general rebate equation of the P-fan series will be 1 over wavelengths. When you have rebate constant, this is 1 over 25. 1 over 25 minus 1 over what? 1 over n2 squared. So this is the response. This is the general formula of the rebate equation in P-fan series of the hydrogen spectrums. Wonderful, wonderful, wonderful. Okay, so that's a piece of information that which is very important for a pre-Form 5 student or Form 5 students or high school student or advanced secondary school student or a pre-Form 6 student or a Form 6 students. That is a good news for you to hear it. So with respect to session 4, let's label this as example what? Because if I check in the previous example 8, example 9. Okay, so let's call this example. Let's just number this as example 11 and refer the book called the Conceptual Chemistry. It is enough for the foundation I built to you. Conceptual Chemistry, this one, Conceptual Chemistry, or we call it Chapter 1. Call it Chapter 1. Okay. Page. Can check page 157. Page 157. So let me write a question, please. What is, and then teach you how we can solve it. What is the energy? What is the energy? Or what is the wavelength? Excuse me. What is the wavelength? What is the wavelength of light? Of light emitted when the electron in a hydrogen atom undergoes transition from an energy level with n is equal to 4, to an energy level with n is equal to 2. What is, okay? Second question is not relevant. So wonderful. That's the question we have, ladies and gentlemen. Wonderful questions. I believe that you enjoy the beauty of advanced chemistry. We're enjoying the beauty of general chemistry, we're enjoying the beauty of the atom, we're enjoying the beauty of Riemann equation of hydrogen spectrum. Isn't? Tell me in the comment sections, please, because I want to know. So let us read the question again together. What is the wavelength? So the question asks us what is the wavelength of what? Of the light emitted when the electrons in a hydrogen atom undergoes transition from an energy level with n is equal to 4 to an energy level with n is equal to 2. What does this mean? This means that when n is equal to 4, it means that when these electrons has fallen from n is equal to 4 to n is equal to 2, hence, you know, n is equal to 2, what its name? Its name is Balmer series. So n is equal to 4, it's the second line of the Balmer series. So you have to recall the solution. Okay, the question didn't mean that the question didn't ask us, but the first step, we said that the spectral lines, the spectral lines are what? Are Balmer series. Spectral lines are Balmer series when n1 is equal to 2. Balmer series. So the second step, we call what? We call the Riemann equation. So the Riemann equation, this is 1 over wavelength is equal to Riemann constant, and then say 1 over n square minus what? 1 over n2 square. Okay? So for this case, we say that n1 is equal to 2, and then 2 is equal to 4. We are looking for the wavelengths. 1 over wavelengths. So we say that after recalling that once we go for the same step, we say that compute the wavelengths. So 1 over wavelengths is equal to Riemann constant, and then say what? 1 over 2 square minus 1 over 4 square. So this makes what? 1 over wavelengths, then Riemann constant, which should be given, or you can use the constant from the scientific calculator. 2 squared is 4, and then minus what? 1 over 16. So then you can use the scientific calculator, or you can use simple algebra of finding the LCM, which is 16. This will make 4 minus 1, and this will make what? 3 over 16 times Riemann constant. So the Riemann constant should be given from the question, or you can use the one, if it is an exam, you'll be given the Riemann constant. Okay, so the Riemann constant is what? 1.097. 1.097 exponent what? Exponent 7 meter. Exponent 7. Exponent 7. Exponent 7. So it is what the unit of it. So the unit of it is what? It is per meter. It is per meter. Okay. So 1 over wavelengths right now means we have this expression 1 over wavelengths is equal to 3 times Riemann constant over 16. So it goes multiplication. So you find that 3 times Riemann constant times wavelength is equal to 16 times 1. So when you make the wavelength the subject, this is equal to what? So this is equal to 16 over 3 times Riemann constant. So this will make 16. When you have 3, Riemann constant is 1.09, 1.097 exponent 7. But this is what? Per meter. So ladies and gentlemen, in terms of unit, this will be 16 of what? 3 times 1.097 exponent 7, and then 1 over per meter. 1 over per meter, so it means that 1 over per meter, this is equal to what? To meter. So we have to use the scientific calculator in order to find the wavelength. So you have to take your scientific calculator. So you have 16 over 1.097 exponent 7. So the wavelength is 8.12. Okay, over 3. So it is 2.7. Wait. We have 3 times 1.097 exponent 7. So then we have 16 over the response. It is 2.7 exponent negative 7, isn't it? Over 4, it is 4 times 1. Yeah. So it is 3 over 16 here. Yeah. So the wavelength so it is 16 minus 4, it is 12. 3 over 16. Wait. So 3, I'm looking for this computation here. So 3 over this one. So here's 16. Over that response. So 16 minus 4 over 64. The answer is 3 over 16. Because 3 wavelengths. So it is 3 times this over 16. To be 16. What happened? 3 times 1.097 exponent 7. Then we take 16 over the response. Yeah, wonderful. Now we have got the right answer. So it means we say wavelength, for this case, it is 4.86 exponent negative 7 meter. So you can also express wavelength. Remember that 1 meter is equal to 1 exponent 9 nanometer. So wavelengths in these cases are mostly expressed in nanometer. So if that's the case, we say that the wavelengths, okay, so we have to change, or we have to express this. So we say that if 1 meter is equal to this one, here you have 4.860 exponent -7. This is equal to how many nanometer? Okay? So if you multiply, we find that the wavelength is equal to 4.860 exponent -7, but also this is equal to 486 nanometer. Right? So therefore, the wavelengths, also being asked for a wavelength of light. So the wavelength of light is 486 nanometer. And the response for that question, I believe that also you got it. Okay, so that is the first example. I have to do a few examples, then I'll leave the homework for you so that you can go further as well as you can. Okay. So again, we have to solve example 12 of hydrogen spectrum. This is, you have to refer the book called the Atomic Structure and Bonding. Refer the book Atomic Structure and Bonding, written or authored by written by a Tanzanian called Gaiza, and you have to check page 7. Page 7 of the book. So let us solve this question. Calculate the wavelengths of the first line in the Balmer series. Calculate the wavelengths of the first line. In Balmer series. When the Riemann constant is 1.097 exponent 7 per meter. So you have to know what the meaning of the first line of the particular spectrum. Okay? So you have to calculate the wavelength. The question is great, but just the technique, if you read the question, is you have to understand the meaning of first line in Balmer series. So solution. Should not waste your time. Solution. So solution is say that the first step, you have to define it. The first line, Balmer series, the first line in Balmer series, is what? This means N1 is equal to 2, that for Balmer series, and the first line is when N is equal to 3. Second line in Balmer series will be the line with n is equal to 4. Third lines in Balmer series will be the line with n is equal to 5. Fourth line in Balmer series will be when n is equal to what? When n is equal to 6, etc., etc. So the first line in Balmer series means n2 is equal to what? To 3. That's the meaning. If you have been asked to calculate the wavelength of the second line in Balmer series, then you have to use the equation. So the second state, we say that we call what? We call the Riemann equation. Okay? The Riemann equation. The Riemann equation states that 1 over wavelength is equal to Riemann constant 1 over n1 square 1 over n2 square. Alright? Good. So if that's the case, we say 1 over wavelength is equal to what? Riemann constant, we know it. It's 1.097 exponential 27. Then we have 1. And 1 is equal to 2, so we square. And 2 is equal to 3. So it will be 3 squared. So just to simplify, to find the expression first, we can just restore the value or the symbol of Riemann constant. And hence this is what 1 over 4 minus 1 over 9. So let us simplify. Okay, so we say that we're calling that the steady state. Say that let us compute wavelength. So 1 over wavelength is equal to Riemann. Then here the LCM is 36. Then we have 9 minus 4. So this will make 1 over wavelength is equal to Riemann constant 5 over 36. So then, if that's the case, we have to cross multiplication. So when we cross multiplication, 1 over 36, this is equal to 5 wavelengths times Riemann. So we divide by 5 times Riemann constant and divide by 5 times Riemann constant. So wavelength is equal to 36 over 5 times Riemann constant. So this is 36. Here we have 5 times 1.097 exponent what? Exponent 7. Exponent 7. So the wavelength for this computation, but this will be, because the Riemann is, here we have per meter, so 1 over per meter is equal to meter. So now you can take your scientific calculator. If you don't have or you lost one, you can order in Tanzania online advanced library. We have original scientific calculator and we are selling them with a very affordable price compared to the price in the different regional local shops or local stationaries. So I ask you, and I will ask you, my dear student, make sure that you got the descriptions of this video and you place your order. It means you look for the links that will send you into the video that explaining different scientific calculators and their price. Okay? So make sure that you do that, and then we'll meet, and I will make sure that you receive original scientific calculator with a guarantee, a special Casio. This is Casio function 991. And also you have to make sure that you pay for the shipping cost. Okay? So in this case, we say that, okay? For this case, we say that, so you have to take the 5 times 1.097 exponent 7. So then 36 over response. This is 6.563 exponent negative 7 meter. But remember that in the spectral lines, the wavelengths of the spectral lines of hydrogen in hydrogen spectrum is expressed in what? So this is expressed mostly expressed in nanometer. Okay? So I've given you the relationship between nanometer and meter. So we go for the OT. This will be the first step. However, it is option. This first step, remember it is what? Option. It's not mandatory. You can just conclude that one. So we say that 1 meter is equal to 1 exponent 9 nanometer. So now we have what? 60.563 exponent negative what? 63 exponent negative 7 meter. We change it into nanometer. So we cross multiplication. So x is equal to what? So this one is equal to 60.563 exponent negative 7 meter times what? Or use times what? Times 1 exponent 9. So with this one we say the value of x, which is the wavelength of the wavelength of the first line in Balmer series. This will make 656.3 nanometer, because the 9 same base are exponent, negative 7 plus 9 is equal to 2. So therefore we say the wavelengths. Okay, the wavelengths of the first line in Balmer series. Balmer series is what? 656.3 nanometer. So that's the response. Wonderful. Okay, so let me teach you how you can solve the next example and then I'll leave the homework for you so that you can go further. So example 13, at least let me do the conceptual question. You may do the rest of the questions, just straightforward. Okay, so example 13, then this right concept. So you have to refer the book, the same book, page 67. 67. So 68. This is 67. The first one was not 67. It was 35. So the first one, 35. This is page 67. So if the wavelengths of the first member, of Balmer series in hydrogen spectrum, hydrogen spectrum is 6,563 angstrom. Calculate the wavelengths. Calculate the wavelengths calculate the wavelengths of the first member of the Lyman series. Of the first, so another vocabulary. In the questions is not underlined, but I underline myself, the first member of the Lyman series. The Lyman series. Okay. So these are the concept questions. The Riemann constant is not given, but we can solve that question without the constant because we know we know on how we can use the simultaneous equation to solve different problems. Okay, so this example 13 is the conceptual. If the wavelength of the first member of the Balmer series in hydrogen spectra is 6,563 angstrom, calculate the wavelength of the first member of the Lyman series. I would like just to do at least 5 questions. So I had from my heart that I have to add in another example, another solved example, example 14, and example 15 will be your homework. At least if you have 5 questions in your mind, you'll be competent to solve any problem about the hydrogen spectrums. Because after this one, we are done with hydrogen spectrums. I'll teach about quantum theory. Later on, I'll teach about Dalton's postulates, Rutherford postulates, and the etc. Then we'll be covered. We'll have covered about the atomic structure. Then we'll go for the chemical bonding. Okay. So if that's the case, we say that if the wavelength of the first member of the Balmer series in hydrogen spectrum. So solution. First of all, there in the previous questions, we have learned a vocabulary called the first line in Balmer series. Today we don't have a word line, we have member. So means if the wavelength of the first member of Balmer series, so it has been mentioned why Balmer series or why a spectral series has been mentioned in order to help you to know the value of N1, to know the ground level for that spectral lines is what is equal to what value in hydrogen spectrum. So we've been given its wavelengths. Then calculate the wavelengths of the first member of Lyman series. Okay? So solution. So the first thing, if you check the data given from the question, data given, first of all, we've been given the wavelengths of what? Of Balmer series. The wavelength of Balmer series is equal to 65, 63 angstrom. You have to change tetometer, or we live in terms of angstrom. So the other wavelengths we'll find also in terms of angstrom and the principle. Okay. Again, we'll be given, so because it is Balmer series, so we say N1 of what? Of Balmer series is equal to 2. Okay. Then we've been told that the first member, so first member of Balmer series is the same, has the same meaning, or the same line with first line. Okay, with first line. So the first member of Balmer, this implies that N2 is equal to 3. First member of the Balmer is when N2 is equal to 3. The second member of the Balmer when N2 is equal to 4. Third member of the Balmer when N2 is equal to 5, etc., etc. So that's another piece of information that will be given. So that's all about Balmer. So when we come to the Lyman series, we'll be given some information. The first piece of information, we know that for the Lyman, N1 is equal to 2. Again, we have been told that you have to find the first member. So we know that the first member of Lyman series is when this is formed when electrons falls from the second energy level where n is equal to 2 to n is equal to 1. So the first member of Lyman series, this implies that N2 is equal to 2. So wavelengths, which is lambda, this is what required. Okay, required. So that's the first step. So we go for the second step. So the second step, let us record the general Rieberg equation. So when we record the general Rieberg equation, we have what? 1 over wavelength is equal to Rieberg constant. We have 1 over n1 square, 1 over n2 square. That's the general equation. So now we say that the Rieberg equation for Balmer, so second step, we say for Balmer, the Rieberg equation now will be 1 over wavelength. 1 over T. So 1 over wavelength of the Balmer is equal to Rieberg constant. Then we have 1 over what? N1 for the Balmer series is 2 minus N2 for the Balmer series is what it is. For the first series it is 3 squared. Okay? To 3 squared. Yeah. So this will make what? So this will make Rieberg constant. And then say what? 4, then 9, this is 36. It's at 9. No, 36. The LCM will be 36. Then we have 9 minus 4. So 1 over wavelength of the Balmer series is equal to what? 5 over 36 of the Rieberg constant. So this is first equation. Okay? That is the first equation. So then we go for the first step. The first step, we say that Rieberg equation for the Lyman series, say 1 over wavelength of the Lyman Leti, lambda L is a wavelength of the Lyman series. This is Rieberg constant, 1 over 1 square minus 1 over 2 square. So this is equal to Rieberg constant. Then here we have what? 4. So 4 over 1 is 4 minus 1. So 1 over wavelength of the Lyman series, this is equal to 3 over 4 Rieberg constant, and this makes equation 2. We don't know, we are not given, in this question, we are not given the value of Rieberg constant. Should not worry, because we have two closely related equations. We know the value of wavelength of the first member in Balmer series, but we don't know the values of these wavelengths. So we go for the what? My beloved students, the first step. The first step, we say that we have to take equation 1, then divide by what? By equation 2. Okay? By equation 2. So let me give that reference because it will be easier for me to write another question. So I'll be writing question here and we using the first and second columns to solve. So with division we have 1 over wavelength of Balmer over 1 over wavelength of Lyman. This is equal to what? Is equal to 5 over 36 Rieberg constant. And here we have what? We have 3 over 4 Rieberg constant. So Rieberg constant cancel. Right? So if we divide this becomes wavelength of the Lyman over wavelength of Balmer. Just do the normal division because this one becomes numerator and this one still a denominator. So then similarly to these values, it will become what? So 5 will remain at numerator, 4, this 4 becomes numerator, and then 36 is the denominator times 40 times 3. So we are looking for the wavelength of Lyman series. So this is equal to 20 of what? Over 36 times 9 times 3. 3 times this one is 18. We keep 1. So 180. 180 times wavelength of what? Of Balmer series. Wavelength of Balmer series. So the wavelength of the Lyman series, this is equal to it. So you can keep simplifying. By 2, can you go 4 by 4? So by 2 we have 10, and by 2 we have 10, by 2 we have 54, by 2 we have 27, then by 2 we have 5. So this will make 5 over 27 wavelengths of Balmer. Why? because this is 9, okay, 10, yeah, it is 4. So simply we say wavelength of the first member of Lyman is 5 over 27 plus wavelength of 40 Balmer series. We know the wavelength of the Balmer series. The wavelength of the Balmer series is given in the question. So we say the wavelength of the first member in the Lyman is equal to 5 over 27 multiplied by wavelength of 40, wavelength of the Lyman, which is 65, then 63, and just 2. So therefore, we say wavelength of 40, wavelength of Lyman. You have to use your scientific calculator. So you take what? You take 5, you multiply with 65, then 63 angstrom. You divide with 27. The response is 32.8. Wait a moment. 65, 63 angstrom multiplied by 5 over 27. The answer is 1.22 exponent 3 angstrom. So the answer is 1.22 exponent 3 angstrom. So simply the wavelength of the Lyman, we said this is 1,000. So put in 3 decimal places, maybe 1.5, the way it is, then 15 angstrom. So therefore, we say the wavelength of the first member of Balmer of Lyman series. Lyman series is 12, 15 angstrom. So that the response for that question. Wonderful. I'm about to end this session. Okay. So let me give you whenever I look any question here, it is concept. Okay, let me do one question for the frequency. So now, if I ready at 8, case you feel from your heart that you want to offer God your feelings and thanksgiving for this program, please don't hesitate, but you may send your feelings and thanksgiving through the telephone number 0759 745331. Okay? So in this example, we say that we have the far. So this is exercise what? Digging deeper exercise 2. So exercise 2, I want to encourage you. I want to solve question 2. So when you have time, I will solve even some other, but this will be enough for you. Calculate the frequency and wavelength of the spectral line of hydrogen corresponding to transition of electron from n is equal to 6 to n is equal to 3. That's from an A. From B, in what region? In what region of the electromagnetic spectrum? Of the electromagnetic spectrum with this spectral line be? With this spectral line B. Spectral line B. Okay, so we have almost these 3 questions. Okay, so we have 3 questions. So we've been asking 3 questions in 2 questions in Roman A and 1 question in Roman B. But don't worry, I believe that right now you can solve this problem within few minutes. So for you to be notified or for you to challenge yourself, you can pause the video and then you try to solve these problems yourself. Then you come and check the solution. So calculate the frequency and the wavelengths. Oh, I forgot. Excuse me. And wavelengths. I was saying that in Roman A we are asking 2 terms, but unfortunately we are asking only 2 terms of the spectral lines of hydrogen spectrum or hydrogen. This is hydrogen. Hydrogen corresponding to the transitions of electrons from n is equal to 1, from n is equal to 60 to n is equal to 3. So the first step, we have to list the data or to check the data given. First of all, this is the higher energy level, so it will be equal to N2, N2 is equal to 6, and N1 is equal to 3. So because the value of N1 is equal to 3, you know that these spectral lines will be, these will be in which region? Okay? So that's the first step. So Riemann constant is not given, but it's known. So here we have to give you a Riemann constant is equal to 1.097 times 10 power 7 per meter. So this is 1.097 exponent 7, 10, exponent 7 per meter. So the second step we have to recall what you recall the Riemann equation. So to recall the Riemann equation for the wavelengths, you say 1 over wavelengths is equal to Riemann constant. Then we have 1 over n1 square minus 1 over n2 square. Okay. So then we say that if that the case, we can find now the wavelengths. 1 over wavelengths of the Paschen series. Riemann constant, we introduce it later. So you have 1 over 3 square minus 1 over what? Over 6 square. So in this one, set a 6, this is 9. So the LCM is set a 6. 6 times 6, it is set a 6. 3 times 3 is 9. So set a 6 over 9 is 4. Minus what? Set a 6 over set a 60 times 1 is 1. But we have what? We have Riemann constant. So 1 over wavelengths is equal to what? Is equal to 3 over set a 60 times what? Riemann constant. Okay, so if we simplify, this will make it, so this will make, yeah, because 4 minus it is 3 over 6, 3 over 6 over 3, 3 over 3 it is 1, 6 over 3 it is 12, times what? Riemann constant. So 1 over 12, so it is Riemann constant. So it means the 1 over wavelengths is equal to what? Riemann constant over 12. Okay, over 12. So we have to cross what? Multiplication. So when you cross multiplication, you get Riemann constant times wavelengths. Get Riemann constant times wavelengths. Okay? Wavelengths times Riemann constant is equal to 12. So wavelengths is equal to 12 over Riemann constant. So this will make 12, but not in meter, okay, or per meter. Okay, so this 1.097 exponent what? Exponent 7 per meter. So this is what? Wavelengths. So we have what? So 12 over that one. So you just use your scientific calculator to get the response. So it is what? It is 12 over 1.097 exponent 7. Response is 1.094. 1.094 exponent negative 60 meter. Is it true? Let me prove again. Here set a 6 over 3, 12 over constant 16. So 1.94 is negative 6 meter. So wavelength is equal to, if you change into angstrom, this is equal to 1094 angstrom. So therefore, we say the wavelength or spectral line. Spectral line is 1094 angstrom. Then we have to answer for Roman B. So because electrons is being translated or is being translated or is being transitionated from n is equal to 6 to n is equal to 3. N is equal to 3, it's what is Paschen series. So because it's Paschen series, so in what regions of electromagnetic spectrum with the spectral line B. So we say the spectral line B would be in what? In Pascal series. And this Pascal series, it is infrared. It is infrared what? Light. Case of the spectrum. So it is Pascal series in infrared light. Okay. So this will be example 15, the last one. And this is the homework for you. And this is homework for E. So homework for E, same page. Now you have to solve question 6. Remember that I've mentioned conceptual chemistry, the reference books in the session 00, General Introductions of Chemistry. So let me give you a question. Solve question 5. Question 5. Calculate the ratio of the wavelengths with the ratio of the wavelengths of the first spectral line of Lehman and Balmer series. Of hydrogen spectrum. So make sure that you do this problem. It is one of the simplest problems for serious students, especially students. And I thank God, actually. I've been overwhelmed with this information. I wanted to pour out the present and future generation. So I thank God who have created me in His own image and likeness. I give Him all the glory and all the praise for this intensive work. I thank you also. I thank God for you who have joined me from the beginnings of this session. This is one of the longest sessions compared to others because I had the objective, a very specific objective, to make sure that I prepare and teach you so many examples about hydrogen spectrums, because you need these concepts also when you be in Form 60, when you are doing either PCB, PCM, or PGM, or PMC in advanced physics, especially with the chapter called the atomic physics, which is the first chapter in the Form 60 syllabus. So until we meet, I remind you to register yourself by subscribing. In case you feel from your heart that you want to offer your feelings and givings of any amount, please send through this telephone number 0759745331. Share these contents with other Pre-Form 5 students, with other Form 5 students. Tell them the light of advanced chemistry right now is in your hands at any time and any day. Please submit your homework in the comment section. In case you have any questions, please use the comment section in order to ask your questions. So thank you very much. I love you so much, and God loves you so much. And we thank you once again to join me. This is Sir Andy. This is Sir Andy, Electronics and Telecommunication Engineer, Olenjolai Moko Dayelo Singo, from beautiful country Tanzania. I would like to say, see you again in session 4F. Don't miss it. Invite your friends. Enjoy the moment.